Hello everyone. We are going to do a problem, maybe two, depending on how long this takes. Okay, so I'm checking the time right now. I have a 15-minute time limit as of yet on YouTube. And when that alleviates, I can do longer problems. So I have a timer set off to the side. This is problem number 5 off the spring 2019 exam. And if time permits, I'll do problem number 11 as well. An air-filled parallel plate capacitor is connected to a battery and 80 joules of energy is stored in the capacitor. Okay, so we have Q equals CV. We have E equals 1/2 CV squared. So there's our two equations we have to deal with this. Okay? And we also have C equals K epsilon naught A over D, because I get the feeling we're going to do something to it. Might have to deal with the dielectric. Anyhow, we have 80 joules of energy stored in the capacitor. The capacitor is disconnected from the battery, and without any charge leaving the plates, the separation between the plates is doubled. How much energy stored in the capacitor after separation is doubled? Okay, so Dr. Ford has an alternative energy equation, and I'm going to find it real quick because we do have his formula sheet at the end of this packet here. Okay, he says energy is Q over epsilon naught A. He has that equation there. Let me go back to the equation sheet because it should show up on the camera. That's the wrong one. That's not the energy stored in a capacitor. We have to use the energy stored in a capacitor. It's 1/2 QV. Right here. It's 1/2 QV, or Q squared over 2C. Or 1/2 CV squared. So it's Q squared over 2C that I want. This is wrong. So E is Q squared over 2C, or 1/2 CV squared. So there's my energy equations that I'm dealing with. Okay? Now, since the charge is constant, I'm pretty sure I should be using this part of the equation right here, since the charge is constant. Now, it says the distance between the plates is doubled. Then we have C equals K epsilon naught A over D. D, not 6, D. Now, the separation between the plates is doubled, so I'm going to double the separation on the bottom. So if I'm multiplying the bottom of this thing right here by 2, that means my new C is 1/2 the old C. Okay, so my energy equation, we're keeping Q constant, and down here we're putting a 1/2 C in there. Now the 1/2 and this 2 are going to cancel out, and I get Q squared over C. So essentially the energy is going to double, because we're losing the 2 on the bottom, so the energy doubles. And we originally had 80 joules, so we have 80 times 2, which is 160. So there you go. We now have 160 joules on that capacitor, and the answer to that one should be B. Okay? So there's number 5 done. It was quick and simple because it's kind of a theory problem. Let's look at number 11 and see if I can do that one pretty quickly. I probably picked out something I can't do quickly for fun. But, you know, I've got 10 minutes left to this video. Oh, yeah, I can't do this one too quickly. I will try. I'm going to pull the camera back some, too, because there's not going to be enough room on here. Now, we did one like this during the review, so there's nothing new here. Okay? Just the charges are arranged a little bit differently. It says, as shown in the sketch, the point charge Q1 is positive 4 times 10 negative 9th. So in my picture over here, right here, I have Q equals plus 4 times 10 to the negative 9th. So I have plus 4 right here. Okay. And Q2 is over here. This is negative 8 times 10 to the negative 9th. And we know the distance here is 0.4 meters. The distance up here is 0.3 meters. The typical distances that this teacher prefers to use. Okay. And what I want to find are the X and Y components of the electric field at the point up here at P. So we're going to have E1, which is KQ over R squared. or 9 times 10 to the ninth. Q1 is 4 times 10 to the negative ninth. And the distance here, it's a 3, 4, 5 triangle, so this is 0.5 over 0.5 squared. Now keep in mind, we're supposed to be doing absolute values of the charges. We find the directions of this using a free body diagram. So we'll come back and do that in a moment. So grabbing my calculator here, validating OS. That's always fun to have when you turn your calculator on. So turn my calculator on, 9 second e to the ninth. Let's make sure we're on screen just slightly off. Times 4 second e to the negative ninth. And we're dividing it by 0.5 squared. I get 144. So the electric field due to point charge 1 at P is 144 newtons per coulomb. Now we're going to go through and do the electric field due to point charge 2, which is here. This is Q2. This one was Q1. So E2 is KQ over R squared, or 9 times 10 to the ninth, times Q, which is 8 times 10 to the negative ninth. Remember, there's an absolute value on that, so the negative sign goes away. And my radius is 0.3 squared, so we can plug that in and get a number. So I'm doing 9 to the ninth times 8 to the negative ninth, and we're dividing that by 0.3 squared. And I get 800 on this one. Okay, so I got my magnitudes. So what I'm going to do now is draw my free body so I can figure out what's going on at point P. Here's point P. I have Q1 over here, and I have Q2 over here. Now, Q1 is positive, so we have a positive charge over here. That means the electric field due to point 1 is going to be going off in that direction. Because the electric field's the direction a positive charge would move, positive charges want to get away from this guy, so they're going to try to go that way. All right? E2 is a negative charge, so the electric field for E2 is going this way. Now when I go to do my components, I'm going to have to find angles for E1. So E1 is going to get components. Now this angle theta here is related to the 3, 4, 5 triangle with 0.4 here, 0.3 here, and here's my theta, 0.5 here. So cosine theta is 0.4 over 0.5, so I can find my theta. Okay? So if I do inverse cosine of 0.4 divided by 0.5, I get my angle is, and we're in radians, that's not a good thing. So I'm going to push mode and get us out of radians. We sure are in radians. So let me do that again. I get 36.86 degrees. Okay? So now making a vector table out of this, because that's what we're going to do to get our answer. We have x, y. We have E1. E1's going to have sines and cosines on it. The x component E1 is going to be cosine. The y component is going to be sine. We know this is cosine because we're adjacent to my angle. So my x component E1 is going to be 144 cosine 36.8. Actually 36.9. Now that's positive because the x component is positive. The y component is going to be positive too. So that's 144 sine 36.9. Let's push some buttons on the calculator. 144 cosine 36.9. And that comes out to 115. 144 sine 36.9. And that comes out to 86.5. I'm a little off on the screen, sorry. 86.5. Now E2, he's very simple because he's only in the positive, he's only in the negative y direction. So his x component 0, and all this 800 newtons, which is up here, all this 800 newtons per coulomb is in the negative y direction, so negative 800 here. To get my answer, we just add down the columns, so this would be 115. And over here we have negative 800 plus 86.5, and that comes out to negative 713.5. And there's our answer to the first part of this problem. And I'm running out of time quickly on my 15-minute limit. My second part of the problem, and I've covered up the paper completely and lost the problem. That's no good. There it is. Second part of the problem says, what is electric potential at P due to Q1 and Q2? Okay? So I'm going to redraw the problem really quick. So we have Q1 right here. And again, Q1 is plus 4 times 10 to the negative 9th. We have Q2 over here, which is negative 8 times 10 to the 9th. And we have point P up here. And we have 0.4 here, 0.3 here, and then this distance here is 0.5. Now finding electric potential is different. It's not vectors. So I could just find V1, which is KQ over R, or 9 times 10 to the 9th times Q. Now since we're dealing with scalars, we don't have absolute values on this. So if it's positive, I'm going to leave the charge positive. If it's negative, I'm going to leave the charge negative. And we're not squaring the bottom. That's one of the big differences here. So grabbing my calculator, we're doing 9 times 10 to the 9th times 4 times 10 to the negative 9th. And we're, oops, I did something wrong. Too many times. And we're dividing that by 0.5. And I get 72 volts for V1. V2, that's KQ over R. So it's 9 times 10 to the 9th, negative 8 times 10 to the negative 9th, divided by my radius of 0.3. Okay, so working that out, we get 9 times 10 to the 9th times negative 8 times 10 to the negative 9th. We're dividing that by 0.3, and it comes out to negative 240. And yes, that one's positive, this one's negative. So we keep the signs with them. Now to get my answer, since this is simpler, we just add them. 72 minus 240 equals negative 168 volts. So the answer to part B is negative 168 volts. All right, I hope you all find that useful. I probably went over my 15 minutes. I hope not. I'll split it into 2 videos if I did.